Okay, we're going to solve trig equations of the form y equals a sine x, y equals a sine bx plus c by Jody DeVoe. That's me. Okay, we're going to take a look at our problem. The problem is about the motion of a spring. The spring is attached to a ceiling, and there's a mass attached to the bottom of the spring. So as you pull the mass down, the spring will pull back, and of course the mass will oscillate back and forth. And there's a picture here. So the equilibrium position is here, and if I were to pull this mass down this way, then the spring would pull it back up toward the ceiling, and then it would continue to oscillate back and forth from there. Okay, so we're calling the equilibrium position then y equals 0. Okay, so y equals 0 is the equilibrium position. So the question then states, find the first 3 times the mass passes through the equilibrium position. Okay, so our equation is y equals 5/6 sine 10t minus 0.93. And you can graph that on your graphing calculator just to kind of get a sense of the motion of the spring. But what we want to see is where it passes through equilibrium. That is, at what time is y equals 0. So I'm going to put 0 in for y and then solve for t. So sub y equals 0, and then what we want to know is what t is for the first 3 times. We're neglecting air resistance here, so that means that the spring is just going to continue to oscillate up and down in this particular model. But we just want to find the first 3 times. Okay, so I'm going to let y equal 0, and then I'm going to solve the resulting equation. First thing I want to do is get this sign by itself here on this side. So to do that, I'm going to divide by 5/6 on both sides. So when I divide on both sides by 5/6, I get 0 still on the left-hand side, and sine 10t minus 0.93 on the right-hand side. Okay, so I'm looking at this and it says the sine of something equals 0. And the something is this kind of big 10t minus 0.93 thing. So to kind of simplify this problem, what I'm going to do is I'm going to call this whole inside part here, this 10t minus 0.93, I'm going to call that theta and make it look like a little bit nicer problem to solve. That is, I'm going to solve the equation 0 equals the sine of theta. Now, if I can solve this one, then I can go back and replace what theta is equal to, that 10t minus 0.93. Okay? So focusing now on this equation, the sine of theta equals 0. So I'm asking myself, for what theta will the sine of theta equal 0? Okay, so I go back to the basic graph for the sine curve. And the basic graph for sine looks like this. It just oscillates through one period. I'm going to put another period on here. And it crosses through 0 at 0, pi, 2 pi, 3 pi, 4 pi, and it goes on. So thinking then the sine of what equals 0, that would have to be when theta is equal to 0, pi, 2 pi, and it goes on from there. I only write the first 3 because the question is only asking about the first 3 times. Okay, now let's go back. Remember that I said that I don't have just theta in here. I have actually 10t minus 0.93. So what I'm going to do now is put back what the theta was actually equal to, and that's going to result then in 3 equations. That is, I want to solve the equation theta equals 0, theta equals pi, and theta equals 2 pi. And then I'm going to go back now and replace this 10t minus 0.93 in place of theta in each of these 3 equations, and then simply solve that for t. So I have 10t minus 0.93 equals 0 is one of the equations. 10t minus 0.93 equals pi is the second equation. And then the third one, 10t minus 0.93 equals 2 pi, should give me those first 3 times when the spring mass system passes through the equilibrium position. Now this is just solving a nice little linear equation. So I'm going to add 0.93 to both sides. I get 10t equals 0.93. So dividing both sides by 10 gives me 0.093. So that's our first time it passes through equilibrium. I'm going to go on over here. This is going to be 10t equals pi plus 0.93. Dividing both sides by 10 gives me t equals pi plus 0.93 divided by 10. That's my exact answer. If I need to have an approximation to that, I can put that all in the calculator to get approximately 0.41. Let's take 3 decimals, 0.407. Okay, and then the third one, that would be 10t equals 2 pi plus 0.93. T equals 2 pi plus 0.93 divided by 10. That's my exact answer again. I'm going to put that in the calculator to get an approximate value. And I get 0.721. Okay, now I can check my answers to this by placing these 3 t values back into this motion equation that was originally given, making sure that y is at least approximately equal to 0. Might not be exactly 0 because we've done some approximations here. But you might want to pause and make sure that that's true. Okay, I think if you took the time and checked those, I think you'll find those are correct. So I'm going to go back and circle these 3 as our first 3 times that the mass passes through the equilibrium position. Okay. Let's look at another one in reference to the same problem of the spring. So I'm going to write down my equation again. Y equals 5/6 sine 10t minus 0.93. And let's find the first time when y is equal to, let's say, 0.5. Okay, so let's write that down. Find t such that y equals 1/2 foot. So that's going to be the first time that the mass is 1/2 foot away from the equilibrium position. Okay, so I have 1/2 equals 5/6 sine 10t minus 0.93. I want to again get the sine function by itself on one side. So I'm going to divide both sides by 5/6, which is the same thing as multiplying both sides by 6/5. Okay, so again, dividing by 5/6, same thing as multiplying by 6/5 to get the sine by itself on one side. So I have sine by itself on this side, and then on this side I'm going to multiply 6/5 times 1/2. And when I do that, I get, let's see, that would be 6/10 on this side, or 0.6. Okay, so I'm going to do something similar to what I did in part A. That is, I'm going to make this a little bit simpler looking equation by trying to solve this equation first, 0.6 equals sine theta, where again I've replaced this inside part here, 10t minus 0.93, as theta. Now this one's a little bit more difficult because I can't look at my graph to find out what theta should be because 0.6 is not a nice number. That is, if this was 0 over here on the left hand side, or 1, or -1 for that matter, I could look at my graph very easily and see what theta should be. It's not a special value, special angle value, like square root of 3 over 2, or square root of 2 over 2, or 1/2. So because it does not fall in any of those categories, I need to use the inverse sine button. So I'm going to use inverse sine on my calculator. I'm going to say the inverse sine of both sides. So I'm going to say inverse sine of 0.6 equals the inverse sine of the sine of theta. Now that looks really nasty on the right hand side, but the inverse sine of sine just is theta. It's like taking the square root of x squared. The square root of x squared is just x. In the same way, the inverse sine of sine, those are inverse functions of each other, like square root and x squared are. You just simply get back to theta on the right hand side. Now on the left hand side, I need to pick up my calculator and use the inverse sine button. Make sure you are in radian mode. I'm talking about t here as time, not degrees, not as an angle. So I need to make sure I am in radian mode. Okay, so go to your calculator, push the inverse sine button for 0.6 and see what we get. Okay, so I find that theta is equal to, let's see, 0.6435, I'll call that 0.644. Okay, and now I'm going to do the same thing as I did before in part A. I'm replacing this theta with what it started out to be, 10t minus 0.93. So I'm solving the equation 0.644 equals 10t minus 0.93. So to solve this, I'm going to add 0.93 to both sides. I get 1.574 equals 10t, and then solving for t, I get 0.157. Okay, and again, you can check your answer. I think we'll find this is the first time when the spring mass system is a half a foot from the equilibrium position. Okay, let's look at one last part here. Suppose I wanted to find the second time at which the spring mass system was half a foot from equilibrium. Okay, so find the second time. The spring mass is at half a foot. Okay. Well, you're still solving this 1/2 equals 5, 6 sine 10t minus 0.93. You're still going to proceed in the same manner as we did before. So we'll get to this point, 0.6 equals the sine of 10t minus 0.93. We'll substitute this theta for the inside part here. So I get 0.6 equals the sine of theta. Now, there are several places where the sine of theta is equal to 0.6. The graph that I'm thinking about here, this is what I have in my head, I guess. Okay, and the graph I'm referring to is this one, for this part here. So let's say right here is 0.6. And so when you're solving that equation, you can see I have two places in this picture, but since sine is cyclic, you can see it's going to hit through that 0.6 an infinite amount of times each time the sine curve waves around there. Now when you push the inverse sine button on the calculator, this is the first one you get, which is our 0.644. Okay, so when I push the inverse sine the first time, I get theta equals 0.644 from the calculator. Now, how do I get this second value here? Where does that come from? Well, I'm going to use a little bit of symmetry here. By that I mean, I know that this piece here and this piece over here have to be exactly the same. And I know that where the sine curve crosses through here is pi. So I know that this whole distance here from the y-axis over to here is pi. So, and I know that this distance to here is that 0.644. And what I want to know is what this distance is. Well, I know actually that distance has to be 0.644 because of the symmetry. So I guess my question actually is, how far is it from the y-axis over to there? That's my question. How far is it there? Because that's the t, actually, or actually the theta that I'm looking for. Well, if it's pi all the way across, and that little piece in here is 0.644, then the piece I'm looking for has to be pi minus 0.644. Okay, so one more time I'm going to try to say that. All the way to here is pi. That little tiny piece in here, that's my 0.644. So if I want to know how far this piece is, it has to be the pi all the way to the end minus that little piece, 0.644, gives me the piece I'm looking for. Okay, so the second place it's going to hit then is going to be pi minus 0.644. And that's the second time for theta. Okay, so when I calculate that on the calculator, I get pi minus 0.644 is 2.5. And then again, I go back and substitute theta equals 10t minus 0.93 and then solve for t. So I'll have 2.5 equals 10t minus 0.93 and solve for t. Now we've done that a couple of times. That means I'm going to add 0.93 to both sides and then divide by 10. So I think you'll find that t is equal to 0.343. And that should be the second time that the spring mass system is at a half a foot from equilibrium. Okay, and I think we'll call that done. I hope this was helpful.